Hello everyone, my name is Tiffany Roberts and this is my Lab 1 presentation. This lab was about observing an object in motion at a constant speed and in a constant direction, in other words, at a constant velocity. This special case is measured using two different methods, one using tracker to visually observe the motion and create data points across instances of time, and the other using GlowScript to create a computational model based on Newton's laws. Newton's first law states an object in motion will stay in motion while an object at rest will stay at rest, when the net force acting on an object is zero. Newton's second law takes into account the net forces acting on an object to predict the object's velocity and position at later times. Going into my observed data using tracker, we were told to record and observe an object moving at a constant velocity. In this case, I used a presumed perfectly flat table and a soccer ball rolled across the table. In order to break down its motion, I had to assign various center of mass data points in each frame of motion that I observed the ball to be in constant velocity, flipping out the ball starting from rest. I chose for the ball to be moving along the positive x-axis. The graph on the right demonstrates a position versus time graph using the data points shown in red in the left picture. Moving into my computational data using GlowScript, this method, unlike the observed method, used initial conditions provided by the data from tracker to create a prediction model. Looking at the left picture, the green dot represents the origin, the purple represents the soccer ball, and the blue line represents the path the ball took from the origin, so we can see that it matches our thoughts of a ball rolling on a table. The plot further reinforces our experiment by showing a straight line, which is consistent with constant velocity motion. I wanted to make sure I point out some important aspects of the coding. The ball's mass is set to 0.45 kilograms. Here the ball's initial velocity and initial position are defined directly from the tracker data's first two data points, and knowing that the clock starts at t equals 0 seconds. The total time the ball traveled was 1.133 seconds. So the while loop includes all time up to this point. It's extremely important to note that the net force acting on the ball is set to 0, and within the code, Newton's second law is utilized by continuously updating the ball's velocity and the ball's position while within the while loop. The ball's mass is 0.45 kilograms and was included in the coding. But does the ball's mass really matter? Mass is a key component to Newton's second law and its equation, but changing the mass to something other than 0.45 kilograms would not change the outcome of this experiment. Why? Well, the net force acting on the ball is also important to Newton's second law, and for this experiment, the net force is 0. So, unless there is some non-zero value for the net force acting on the object, mass doesn't affect your result. Here is a results comparison showing both the data gathered from tracker, the orange line, and the data predicted using GlowScript, the blue line. As you can see, there is a slight difference. Possible reasons for this may include that the ball is traveling out of plane motion. It may have been rolling slightly in a direction other than solely along the x-axis. Also, if the table wasn't perfectly level as I had assumed, the ball may have sped up. Both are instances I would try to improve upon if I did redo this experiment. Leading into a question, when I analyzed my video data in tracker, I made a choice of the orientation of the axes. How would the results change and how would they remain the same if I were to flip the time and position axes? Well, flipping the x time and y position axes causes a mirroring of the data across a line at 45 degrees. Here's the original data using the standard coordinate system, and here's the data when flipped across the 45-degree line in order to accommodate the time now being the vertical and the position being the horizontal. However, the correlation between tracker and GlowScript remains the same. Leading into another question, my observations can be predicted well by my computational model when I set the net force equal to 0. Is it possible to say how many pushes and pulls are added together to give 0 net force in the case I observed? Newton's laws only consider net force as a singular value. There are currently no methods for backing out the sum forces that create a net force without directly analyzing a physical system. Thus, in the case of the ball rolling along the table, the two main forces that can be theoretically considered are gravity and the normal force from the table, where both forces are equal in an opposite direction to cancel each other out. In conclusion, this experiment highlights the main aspects of Newton's second law: velocity, both final and initial, mass, time, and the net force acting on the object, all while considering the object's position. It also highlights some huge takeaways. We were told the net force acting on the object is 0. If we had been given a non-zero value for the net force, our results would have been much different. Mass would have played a bigger role in the equation. It also shows how computational models, if provided with initial conditions, can be accurate predictors of physical systems using Newton's second law. It also reveals the differences that can occur between experimental data and computational data due to unconsidered forces or oversimplified equations. This concludes my presentation. Thank you very much for watching.